Last Friday, we stopped at Gauss's law, and that's where we pick up today again. So the essence here is, you remember we were computing the flux through an enclosing surface of a volume. We have a control volume. That control volume has an outer shell, and this basically gives us a virtual surface, and there's a closed surface. And if we integrate over the dielectric field over this surface, then we are basically looking at the flux that is flowing into the control surface and going out of the control surface. And we saw that this control surface, the flux over the control integrated over the control surface was equivalent to the charge which is inside the control surface. And I give you a few examples here how that could look like. For example, number one, you have here a charge of minus 2q and a charge of plus 2q. Now you put some control volume over it. This is our volume, and then we have the enclosing surface. These are our two charges. And if you are taking now, let's make it with a single integral sign because it is implied that is over a surface just by putting here this sign for the enclosing surface, a V here. And we integrate, and we use a vectorial area element, and the result will be minus 2q plus 2q will be 0. So take a second volume control volume, and that shall cover only this one charge here. So this is our second control volume. And the result here will be then, we have another example is we have here a charge of plus 2q, charge of plus q here. This is our control volume, the enclosing surface. What is the integral over the flux over the enclosing surface? So we're taking the dielectric, we're taking here the displacement field, and you see you have inside 2q plus another q, that gives you the total of plus 3q. Add some more charges here, plus q, plus 2q, minus 2q, minus 4q. So you can go here with arbitrary charges, and now we make this our control volume. So what we obtain, we have here integral over the displacement field is the sum of the charges inside the volume. So all charges which have the property that their position, that they're located inside the volume, these we add up. And that would be here this plus 2q, that would be this plus q, and that would be here the negative minus 4q. So minus 4q gives you a total of minus q. So that hence our goal is here to calculate the displacement field here and basically solve the integral over this flux integral. And in the end, we get the sum of the charges included. And what we do is, for that purpose, we need to do an integration in the three-dimensional space over a closed surface. And for the charge, we end up then also doing volume integrals. So this actually then also refers you to the math recap that we did on Friday. So we need an integration in 3D space. We will also need volume integrals that you see in a moment, respectively in the tutorial that we started and that we will finish later on. You will see that. want to refer you also to the math recap. Okay, that brings us now to a further aspect. This far, we have assumed that we had point charges, but it is also very useful and maybe more common than even to work with charge distributions, so charges per volume, as this is better for us to handle in practical applications. So in many technical problems, we rather work with charges per volume. So for example, if you have a conductor, the charges will be given as charges per cubic centimeter. So you have a conductor that has, for example, 10 to the 22 power of 22 charges per cubic centimeter. So this is a number. We give that as a number per cubic centimeters. And for that reason, our point charge concept is a bit limited. You don't want to have 10 to the 22 point charges, 10 to the power of 22 point charges to account for in your calculation. We would have to add up all the point charges from I is equal 1 to n, and our n is in the order of 10 to the 22 per cubic centimeter. So we have carriers, and they always have a certain volume, and they're also distributed in space. And this is a bit in contrast to our point charge concept. Also, it can be useful to take into account the statistics. So that, for example, includes thermostatistics, thermodynamics, also the transfer theory. So it is advantageous for that reason to transition to a continuous charge distribution statistic that, for example, includes here thermostatistics. So these are the things that you would like to consider. And for that reason, we introduce here the space charge density, and that we denote with the Greek letter rho, which looks like that. Yeah, this is we call our space charge density, and this space charge density, you can think of that in some way. In analogy, this is a little bit like a mass density. I mean, it's not a mass density, but you know, densities also from mass densities. There you give, for example, a mass per volume. So just like you give for any mass, any object with a mass, you can also make use of not giving the mass of the complete object, but give a mass density and then evaluate the mass of the complete object by integrating over the volume. You can do that also in a similar fashion with the space charge density. So just as an analogon, consider the mass density, which is kilogram per cubic meter, which is basically a mass per volume. However, our rho is also a function of r, and it gives us the amount of charge in a volume delta V over the volume of delta V. So that's the ratio. And we assume then that this delta V goes to an infinitesimal value. So it becomes a small dV here. What is our unit? The unit of the charge is, as we assume it, this charge is ampere second. The volume is given in cubic meters. So we have a unit of rho that is given in Coulomb per cubic meter. How do you obtain then the total charge in a volume? Well, if you have a constant charge, then you just multiply it with the volume. The general term here would be the total charge in a volume, in the volume delta V, that is then given as the Q is the total charge is the rho times delta V. And if that rho is constant and not depending on position, that means that the rho is not a function of R, then our charge becomes very conveniently just the rho times the volume as a whole. However, in the more general case, we have a rho that depends on a position R. That means we have a rho of R. And then what becomes our charge? Well, the charge is then a function of the volume, and we obtain it by integrating over the charge density over the given volume in this fashion here. This here is an integration in 3 dimensions, so you can also write that here as a rho of R, and you have here the differential element of R to the power of 3. This is our equation 1.28. So you see you have here the situation that our rho depends on R, and hence the total charge in the volume is obtained by a volume integral over the charge density. Now, you can also have a different scenario actually where you don't have a charge density per volume, but you can also have a surface charge density. So the surface charge density, so the volume charge density we denoted with a rho. We use a different letter for the surface charge density, and that shall be our sigma. This is sigma of R. This is a small sigma. And where do we encounter this surface charge? That can be, for example, at boundaries between 2 materials. So occurrence, for example, at boundaries between materials. That means we could have here a material 1 and we have a material 2. And then in between you have a thin layer. This is just basically the boundary. Let's make it like that here. Thin layer. And in this layer here, you may have some charges. The other scenario is where you could have that, which you can have also that both of it. You can have that in a capacitor, but of course also the capacitor can be filled with a material, and also it can be filled with multiple materials. And at these materials, then you can have again interfaces. So then you have that first scenario also in addition to what I'm giving you here right now as an example. You can have a capacitor. These are 2 conducting plates which are connected here so that I can charge them. And you have charges on these plates. And in the end, these charges will accumulate at the surface so that for that reason, I can also work in this scenario also with a surface charge density. I can still, that also the concept of the space charge density, that would be also applicable. So that would be what is more, it's a bit up to me how I model this also. Of course, the charge also has on the microscopic level always a 3-dimensional extension, but because it is so concentrated to the surface, the concept of this surface charge density is a useful one. So I have here 2 conducting plates with opposite charges, and they are accumulated at the surface, and they accumulate at the surfaces. Also, what you can think of is, for example, you have a very thin shell here, then it can be also advantages to work with these surface charge densities. You have a thin shell and you have here charges on it. You can then define a charge per surface area. So our surface charge density is, we said we denote that with a sigma of R, so it's a sigma. And the definition here then of the sigma of R is a charge in an area element. And that area element we denote with a delta A. And the density is then charge in an area element per delta A per delta A. So it is basically charge per area. Thus, what is the unit? The unit of sigma is Coulomb, that means ampere times second, per square meter. Also here you can have two different scenarios. You can have the situation that your surface charge density is not a function actually of the position. That means it is constant. And that means you have over the charge, over the surface, a homogeneous charge distribution. Meaning, if you want to get the charge of an area, you obtain that simply by multiplying sigma times the area. The other scenario is, as we had it also for the space charge density, also here for the surface charge density, you can have a position dependent density. And then you end up with a Q of A, which is obtained by taking the integral over the surface charge density, and then that gives you the total charge on surface A. Again, so we have two scenarios. One is we have this constant, the other one it is position dependent. Then you obtain this by taking here the integral. So previously we have seen how the Gauss laws works for point charges. Then it is working very much analogously for the distributed charges. So remember, we had Gauss's law, taking the surface integral over an enclosed surface, evaluating the flux, and is equivalent to the charge within the volume. Now, again, dV is the enclosing surface of control volume. And the charge per volume that we saw now is actually taking the volume integral over the space charge density, rho, as a function of r dV. And that is the same as this one here. You see that basically you insert that here into the Gauss law. And what do you obtain then? Well, then just insert it. You get the left-hand side remains unchanged compared to here. This is our charge in the volume, and that is, so now you have Gauss law rewritten for the scenario where you have a continuous charge distribution given by a space charge density. So why is this very useful also, amongst other things? With this formulation here, now we can easily calculate what the displacement field or also the electric field, because they're always tightly interrelated, are from an arbitrary given space charge density. So if we apply equation 1.32, we can calculate either our D field or also our electric field, which is the displacement field divided by the permittivity. And we always assume permittivity is, we have a homogeneous and isotropic material, so it is not dependent on the direction of the fields, and is at least locally homogeneous, so not dependent on R. So we can obtain that from the given space charge densities rho of R. Okay. How does it look? when we have charges which are distributed on a surface of a structure. So then we are operating here with our sigma as a function of r. And so you could think of having here some surface S, and on this surface you have a charge distribution. Sorry, here. And now you can again take your control volume, as you do always with the application of Gauss law. So you have some control volume here. This control volume intersects with the surface. This is our volume here, and it has also an enclosing surface. So we have charges which are distributed on the surface S. This distribution is given by the surface charge density, sigma of r, on S. And our Gauss law states that doing the integration over the enclosing surface on this control volume over the flux gives us the charge. So basically we then define, as we have plotted here already, a control volume which encloses where the D field is evaluated. We define a control volume which encloses the volume where the D field is evaluated. So you see what we have depicted here. We have defined the control volume where the charge is elevated. Which charges are now relevant? Well, relevant are the charges which are within the volume. That means basically these charges here. These are relevant. This is basically those which are inside the volume V. What you have here on the surface, but inside the volume. It means we're looking here at the charge which is contained in the intersection of the volume with the surface. So that's basically where we have, this is our relevant surface area. This area, the surface which is contained in the volume, that is what we obtain here when we evaluate our flux integral and use Gauss law. So basically what you get here is Gauss's law. So on the left-hand side, you basically get a flux integral. You see also here that this flux integral requires here that this here is a vector quantity. This here is also a vector quantity, the d. While on the other hand, you have here a surface integral, and your sigma here, and also here the vectorial element, these are basically scalar quantities. So on the left-hand side, you have the flux integral, and this is a vector quantity. This also shows then here. While on the right-hand side, you have here a surface integral. And this was a vector, and this here is a scalar quantity. That shows then also here. Okay, you have questions? So this is basically taking the step from applying Gauss laws to the scenario where we have point charges. We move to the concept of having space and either space charge densities or surface charge densities, which are usually a more practical choice and which allows us to use and look at scenarios which are also this charge, the variation of such charge density distribution allows to have enter some statistics into this. So this is a more practical approach than dealing with the point charges where we address each charge individually. Now I want to show you what happens if we now we have seen here this integral representation of the Gauss law. What happens if we use these control volumes and we let them shrink further and further? We actually get to something which is called the differential form that I want to address. So this far we have seen the integral formulation. So we take the integral over the closed surface, over the D field and the vectorial area element. It gives us the charge enclosed in the volume. Also, it gives us this charge enclosed in the volume we obtain also by taking the volume integral over rho, our space charge density. Remember, this is our control volume. And we have here entering field lines, and also we have leaving field, that are exiting again. This could be our dielectric, but it can be also our electric field lines. They are interrelated through the permittivity. So this here is our volume, and it also has this enclosing surface. This integral here, that left-hand side of Gauss's law, which is standing there, that is our flux integral, right? This is our dielectric, our displacement field. Sorry, this is a displacement field that we integrate over the vectorial surface element, and that gives us the flux integral. And you could say this is kind of a balance of the E field or the displacement field lines entering and leaving the volume that it gives us. Entering and leaving the volume, or exiting the volume, that you could say that is what it means. So what you can do now is to take this volume, your control volume, and actually divide it up into very small volumes. So we have our V, and we divide it in a multitude, let's say I from 1 to n into small volumes V sub I. And for each of these small volumes, you also have some field lines entering and exiting. Now make these volumes smaller and smaller, make that volume V sub I approach 0, and we go for the limit where V sub I becomes 0. Then you take here the flux integral over this volume, V sub I, whatever is entering in terms of displacement field into that volume, and you divide that here by the volume V sub I. Yeah, so you let the volume go to 0, you divide here this integral, this flux integral over this volume also by the volume, and then what you obtain is actually the so-called divergence of the displacement field. This here is actually the definition of the divergence then. I mean, divergence, you don't have to take a displacement field, you can do that also on other fields, but the concept of basically shrinking here, taking a volume and you evaluate the flux through that enclosing surface, and then you divide that through the volume, and you let this volume shrink and go to 0, then you get this expression here. So here you basically have a flux integral for very small or small volume V sub I. The divergence, then the divergence of D, that represents the flux out or into a very small volume element. So either out of or into whatever is the net into a very small volume element, V sub I. If you think about that, what it represents, we have, say, some small charge Q in this volume element, and it will give you D and E field lines out. And this is our small volume V sub I. And if you have locally some source then this divergence will tell you that. So it's kind of a local source strength for the displacement field or the electric field. I put that in quotation mark. This is what you could understand for the meaning of the divergence of the D field, respectively also of the E field. So if the divergence is vanishing, that means there is no source, there's no net Q or net minus Q, so there's no net Q in this infinitesimal small volume element. So the divergence of T tells you something about the locally distributed sources and sources respectively. You can call it also a sink. Sink is where the field line will end. Source where will it originate for us. That would be a source will be a positive charge and a sink will be a negative charge. It tells you something about the locally distributed sources, respectively sinks of the D field, and distributed sources, respectively sinks. That means this is given by your space charge density, rho of R. So you see, we have gotten an insight into the concept of the divergence. So we can reformulate also our Gauss law into this differential form. So again, let's put down Gauss law, flux integral. And on the left-hand side, on the right-hand side, we have the volume integral over the surface, over the space charge density. And this is what we call Gauss law that we have said already, but this is in integral formulation, yeah? This is what we have used this far. It's the integral formulation, obviously, because you have on either side an integral. You have here an integral quantity, which is the flux of the D field through the enclosing surface. And you also have here an integral quantity that is a total charge inside the volume. So this is an integral quantity. Also mind the displacement field is a function of R. Also the space charge density is a function of R. So these are both position dependent quantities. So you have a local formulation. So I have to make some more room again for my notes. So now we can apply the Gauss integral theorem to the Gauss law, and I'll show you what that means. So this is evaluation of the flux integral. Basically here we're entering now with our integral theorem. We can also express it as a volume integral over the divergence of the displacement field, and that gives us here unchanged from Gauss law on the right-hand side, the volume integral over the space charge density rho of R. So basically we say that the dV should be very small. And if we get to the point where it is really small, then actually we can skip the integral. So you see if you look at the definition here of the divergence, we have here obtained the divergence by letting this infinitesimal volume V shrink that always further and further when we take the flux integral and we divide this flux integral through this volume element. So you see, if you compare that, if we want to get the quantity of that flux over the enclosing surface, we can also integrate, instead of just over the enclosing surface, over the entire volume, and integrating over the divergence of the displacement, the displacement field. So now you have seen, you instead of integrating over the surface, you integrate over the whole volume, but you integrate over the divergence rather than of the displacement only. And now if you think that your volume actually is very small, you get to that point where you actually can skip the integral and can make the statement that your divergence of the displacement field is equivalent to the local value of your space charge density. Are you comfortable with that? With respect to the divergence, some notes, but I put them in quotation marks. So the source of the D field, respectively the E field, are space charge densities. And so these electric fields, or the electric field, you can have a multitude of fields in different realizations, but in any given example, any given space, there's only a single field. And that also is the electrostatic field also. We are here in electrostatics. At that point, the electrostatic field is generated by charges. And with respect here to this, using the divergence of T, I want to also point out that later on, when we get finally to Maxwell's equation, there we also will use Gauss's law in differential form. And yeah, maybe one more note on the side. Okay, you have here your space with a number of charges. These are your Q sub I. You have here a small volume element V sub I. All of these charges contribute here to the sources to the electric field. This whole thing here is your volume. And then you have your surface integral over over the displacement field. We know we can rewrite that here as a volume integral over the divergence, and that gives us the sum of the charges that are within that volume. So the E field is generated Q sub I, and the number, of course, of these Q sub I, that you again obtain by taking the volume integral over the surface, over the space charge density. And what you also see then is that if you go to the ever smaller volumes, so you go to this V sum I, then you get to the point that you can say that your divergence here is your Qi here, your point charge, divided by this volume element. And note on the side, this divergence operator, if you take the divergence on some field, then you know that this is this operator here, you know, the nabla operator we introduced in the recap, partial to partial x, and the next time partial to partial y and partial to partial z. And then you get here the fx component, fy component, fz component. And so this is then partial derivative of the x component of f with respect to x, partial derivative of the y component with respect to y, and partial derivative of the z component with respect to z. And the divergence ends up to be a scalar value that is also important. Oops. Now I want to look at Poisson's equation, and that you obtained actually in a quite straightforward manner. We know that with respect to the scalar potential that we have introduced earlier, that the electric field is obtained by taking the negative of the gradient of that scalar potential. Respectively, we have derived the scalar potential by integrating over the electric field from some reference point to the desired point. That gives us the definition of the scalar potential up to some constant. That's what we said earlier. Now, let's insert that the electric field is the negative of the gradient of phi, and we put that into the differential form of Gauss's law. And also what we make use of is the circumstance that we know that the displacement field is related to the electric field via the permittivity. Insert that. You see here we had divergence of D. We insert here is rho. We insert for D divergence of epsilon, which is the permittivity, times the E field. And the E field, this is actually quite straightforward. The E field we replace now by the expression that gives us, that relates the E field to the scalar potential, that is minus gradient phi, and that is rho. So now we can assume in this instance, so or respectively in the instance where we can assume it, that the permittivity is not position dependent, then we get a simplified formulation. So what we've seen here by inserting this here into Gauss' law, the circumstance that the displacement field is given, here you see Gauss' law, divergent in differential form, Gauss' law, divergence of the displacement field is equal to the charge. We inserted for the displacement field permittivity times electric field, and for the electric field we took the minus gradient of phi. Now we simplify that a bit further. This is now the general formulation, what we have seen here, what is called the Poisson equation, here, Poisson. And now, if it is not position dependent, the permittivity, then we write this Poisson equation as divergent of gradient of phi is equal to minus rho divided to epsilon. So you see the minus, we just shifted to the other side. And because the epsilon is not position dependent, we can pull it out here of the divergence. Otherwise, it would contribute here to the divergence, and we could not do that just like that. But because epsilon has no spatial dependence, we can pull it out of this divergence operator, right? Because you see that the divergence operator here, this is our divergence operator, there is no spatial dependence on the permittivity, so we can pull it out. And you get now this Poisson equation in the simplified form. And we want to introduce here a different formulation for these two operators. We take the divergence of the gradient, and this divergence of gradient, that can be given by this, what looks like a delta, but it is called the Laplace operator, and that is given as partial square to partial x square plus partial square to partial y square. It's our Laplace operator. Sorry, what was that here? And then you get Laplace operator on the potential phi is equal to minus space charge density over permittivity. That's equation 1.37. So that's Poisson equation for the case where your epsilon is not position dependent. It gives you a relation between the potential and the charge distribution. So the Poisson equation, that is, by the way, it's a partial differential equation, and it allows you to calculate a position-dependent electrostatic potential and from the potential also, of course, the electric fields for any given charge distribution. And if you want to solve it, then you need, of course, boundary conditions. And then you can find some systematic mathematical methods for this solution that you find in electromagnetic field theory. And also, these can be done, you can, very general problems, you can then find numerical solutions. For that, you find also special tools like the finite element method. And these are then quite universally applicable. That is different from the integral formulation of Gauss's law, which kind of limits you to special cases. But if you want to have any arbitrary electrostatic field problems being solved, then you will resort to this Poisson equation. And you need this equation plus boundary conditions. Always you need the partial differential equation, and in addition, you need boundary conditions. This is essential to solve for some problem. And then you can, especially once you resort to an implementation for numerical solution, then you can actually use this equation really for any arbitrary charge distribution problem and obtain the electrostatic field. So in that sense, this Poisson equation is a rather important equation. And yeah, you have questions? I have on this gap text sheet also here a reference to the Coulomb potential in Coulomb field charge distribution. This is basically when you have here these point charges, how you obtain the potential. And there I would like to refer you here to the printed lecture notes. This is, it's a small section. You can find these details here, but I will not give you further details, but you find those in the lecture notes. Okay, summing up what we did this morning, we were proceeding with the Gauss law that was yielding us a relation between the flux of the displacement field D and the charge enclosed in the control volume. We had originally done this for point charges. We moved on to implement this also for charge distributions, and these were namely space or density charge distributions. And then from this integral formulation, we were looking what happens if you go to ever smaller volumes, and we were looking for, basically we were looking at what the divergent, how it is defined, and that we said we can split up our volume in small volume segments, make the volumes ever smaller, divide that whole flux integral equation through this infinitesimal small volume element that gives us a divergence. And so as an alternative to the Gauss law in integral form, we have obtained a different formulation which is in differential form. Also that differential form you will find that is useful when later when we get to Maxwell's equations. You can get this in integral form, or you can get this in this more local differential form. And these two formulations go hand in hand. One, you solve the integrals, and in one, you work with the differential formulation. And moving on from there, we found that we saw that Gauss law relating here the flux to the charge gives us means to determine the electric and the displacement field from a given charge distribution. And when we do that for the with the differential formulation, we can also connect that to the scalar potential, and we find here in particular for the case where the permittivity is not varying with position, we find a partial differential equation which allows us for arbitrary charge distributions to find the potential and also hence the electric field. This is a problem that you can in some instances solve also analytically, but this is a formulation which is very suitable also to be implemented numerically based on some methods like, for example, finite element method. And you can very easily with such a tool, once you have implemented it, compute electrostatic fields caused by arbitrary charge distributions and with the given boundary conditions. Now let's get to the electric fields. This is 1.7 between conducting materials. And we have already earlier in this chapter said we can do a classification of materials, and we had 3 kinds. What were the 3 kinds? Anyone? Sorry? Semiconductor? When you named the semiconductor, you probably also named the conductor, yeah? Yeah, the insulator and insulator and dielectric material. Basically, that is one group. I mean, that's a different way of calling them. So yeah, thank you. So this is, we have the metals and conductors, we have the semiconductors, and we have the insulator and dielectric materials. So let's take them down again. Metals or conductors, they have highly mobile charges. Then we have the semiconductors, second group, and then we have the insulators, respectively you can call that the dielectric materials. So these we have also seen in chapter 1.5. So let's think of some conductor here. We have some conductor. So the conductor, that could be some metal. So you have here charges distributed, and actually you have charges of 2 kinds. You have here these positive charges, you have negative charges, and in total you have a very large number of charge carriers. These charge carriers, I made here plus and negative, so you know that the atoms that make up this conductor, they have positively charged nucleus, but there are also electrons around those, and some of these electrons at least are free to move. So these are the mobile charged carriers, mobile charge carriers. Yeah? So you have a large number of those, of mobile charge carriers. That is important. Otherwise, for it to be conductor, we know also the dielectric material consists of atoms that also have positive charged nucleus, negative charged electrons, but they are not mobile. They are bound to that to the nucleus, and they are bound in that structure that constitutes this material, but they're not free to move. So in the conductor, on the other hand, you have a number of mobile charge carriers, which is high, and these charge carriers are the electrons, so the negative element charges. And we are talking about something like 10 to the minus 21 to 10 to the 22 in number per cubic centimeter. Also, in a conductor, you never have an electric field in a perfect conductor. Also, if you look at this graph here, you see these are not so nicely arranged that you instantaneous, okay, it's a sketch anyway, but you would not be able to maybe conclude that the electric field has to balance itself out, but actually that is what is happening. You have no electric field inside there. Also, they are moving around, and so the field is also keeps changing. But any fluctuations of charges, they are cancelled out instantaneously. So if you have any charge moving, you alter, of course, the electric field, but because they're all mobile, any fluctuation of these charges are cancelled out such that there will be no electric field inside the electric conductor. They are cancelled out instantaneously, no electric field. And then you have these negative mobile charges, which are located near the positive charges. But these positive charges that you see here, they are basically fixed. They are fixed, so-called background charges. And you have also in total, the total space charge density is vanishing because these positive charges and these negative charges are compensating each other. So the mobile charge carriers, which are negative, they are located near the positive, and the positive are fixed in position. And as a consequence, the total space charge density is vanishing. This aligns also with that we have no field in there. So rho total is 0. That means the plus charge, and minus charge cancel out. From that, and what we just have seen in the previous section a moment ago, we can say that the divergence of the displacement field, which is given by the spatial charge density, that is 0. And as a consequence, also the electric field is 0 because minus the gradient of phi. So the electric field is 0, and hence also the gradient, this is interrelated, of phi is 0. And for that reason, you also get a phi which is constant. So if you have a conductor, and I'm talking about an ideal conductor, yeah, so you have no electric field inside there, and you have a constant potential. Electric conductors are the electric conductor is an equipotential region. So what happens to the external field? Let's review how that looked like when we had the scenario where we had a dielectric material, basically an insulator, as we have seen in chapter 1.5. You put here a number of positive charges, a number of negative charges. So this is plus Q here, and this is minus Q. The cause for an electric field. And if you have some dielectric material in here, you put that dielectric material into this electric field, and you have basically some small dipoles here in this material, and they will align such that they counteract the external electric field. As a consequence, you get a polarization field, which is counteracting, oriented in the different direction to the electric field. And your electric field inside the material will, there will be some electric field remaining. It will not be vanishing, but it will be reduced, and that reduction depends on the permittivity of that specific material. So we have also the concept of the displacement field, and this displacement field is generated by this plus and minus Q here, and there are no free electrons in this scenario. The atomic charges that you have in your dielectric material, however, they react to the external field. And as you see in this graph here, these negative charges, they move just a little bit. I mean, they're not really free, but they have a small degree of freedom. So they move a little bit, just as you see here, these negative charges move a little bit to the left. And in consequence, you have these electric dipoles that are then oriented. Respectively, if you have atoms, you can also have the case that these are not original dipoles, but as soon as they're in the electric field, these charges being a bit pulled apart, they become at that point dipoles. And these put up this polarization field, which is counteracting the electric field. And as a consequence, you have in this graph here, always, you have a constant dielectric. No, the dielectric is here in this is what your dielectric is. You have a constant displacement field, and the E field is varying here. Within this material, the E field is being reduced compared to the E field outside, where outside the E field is 1 over epsilon naught times the displacement field, and inside it is 1 over epsilon naught over epsilon relative. So no free electrons. Atomic charges react to external field. You can say that the negative charges in this example move a little bit to the left. They move a bit, let's say, a bit to left. And you have here electric dipoles, and you have a polarization field. And that is, by the way, proportional then to the external electric field. Now, for an electric conductor, we again set up the scenario where you have Q plus and Q minus here. And now we put in here an ideal conductor. What happens? So this is our ideal conductor. So you have these positive charges here, which are source for the electric field. And you have negative charges here. And in this ideal conductor, the negative charges will move to this side. Positive charges will move to this side. And if you look at your electric field, then you have this situation that your field lines, where the perfect electric conductor is placed in, the field lines will run into that conductor, and on the other side they will come out again, and you will have inside a secondary electric field such that the electric field inside is vanishing. So you can decompose your electric field basically in the electric field in absence of that conductor and that in presence. And if you superimpose these two solutions, you will. So what happens is basically you have an electric field that is acting on the charges inside the conductor. It will pull the charges such that the charges will cancel out any electric field inside. So you have highly mobile charges, and they can follow the field. In this scenario here, you have the negative charges. They are moved to the left now because of this external field. Negative charges move to the left surface, and positive, they are positive ionized atom. They are, I mean, they are fixed. So basically, you have a lack of negative charges on the right-hand side because the atom, the nucleus is fixed, but you pull away the mobile charges. The mobile charges move to the left, and what you remain at the right-hand side, you have a surplus on positive atoms, and basically you have positive ionized atoms there. The field inside, electric field inside here is 0. And you can now use the concept of the surface charge, sigma r, that is given by the absolute value of the displacement field, because the field, as you can see, at the very right and left border, we have basically some charged plates, which are plane plates, and the electric field lines are all also coming out perpendicular on these plates. So you can say that you have a normal vector here, and the absolute value of the normal vector is 1. And the D field anywhere is always perpendicular to the surface of the conductor. And this phenomenon is called then the electrostatic induction. Very short break, okay? But we don't have so much time, isn't it? Let's make 5 minutes break and then, yeah, okay. I maybe can start to. And so we are quite close to the end of chapter 1, and the other chapters are significantly shorter.
Okay, that's good.
So chapter 2 is rather short. Chapter 4 is very short. 3 is a little bit maybe more, but I think by tomorrow we will should be done with chapter 1. Yeah,
Okay, can.
we have 4 chapters in total.
How do you simplify this part from this, which is A and which is
Oh, sorry. What is this? Is
your 2016 Casio paper? This
okay? Yeah.
the formulas, right? Is it absolute sign or
Yes. Yeah. Okay. Let's resume. Yeah.
it's an absolute sign, right? So let me just be R2 minus R1 over the
Maybe I'll um, s- just address it right now, and but because there was just I had also these questions. The Coulomb force. The Coulomb force. There was earlier a question why you have in these problems appearing that there's a proportion. You have the distance vector. It's and okay, sorry. There was a question regarding why we had that in the problems before, but also it shows up in the solution for one of the exam sample problems that I've posted. Why do you have here the radius to the power of 3? So you remember that the Coulomb law, or the electrostatic force law, tells you that the force is inverse proportional to the square of the distance. And also then when you use that Coulomb law to get your electric field from point charges, you always have also then the electric field. It is inverse proportional. The electric field generated by one point charge will be inverse proportional to 1 over r square. So why do you have this to the power of 3? That is because you have this dependence of being proportional to the distance, the magnitude of the distance vector to the power of 2. Yeah, this is gives you the dependence on how the magnitude is decaying with the law 1 over to the power of 2 with the distance. But in addition, you also want to keep the vectorial quantity because the force is also not directed. It has a certain direction. And this direction is given by the vector, also by the distance vector, yeah? Is also given by the distance vector. And so you get the direction in with this term here that you put in just to get the direction. But now, if you would just leave it like that, you make a mistake because this not just only gives you a direction, this distance vector gives you also a magnitude, and you want to get rid of this magnitude again. So that's why you divide this once more through the magnitude of the distance vector, right? And this gives you 1 to the power of 3. You have to do to the square to account for the um, decay of the force with 1 over the power of 2 of the distance. And this one here is basically um, your this is your direction in which the force is acting. And this is being normalized again to this. So this is why you have 1 to the power of 3 there. You have the, is this clear? Yeah? So when you have this in this Coulomb law or in the, when you, based on the Coulomb law, get the electric field from some point charge, this proportionality you have to the 3 because you have up there this term here as well. So for the electric conductor, you see that the charges have this high mobility, and for that they compensate for any electric field that attempts basically to build up in this conductor. It will be immediately compensated by the charge redistributing. And for that reason, in the electrostatic case, you have the electric field completely pushed out of the conductor. There's no electric field. And for that reason, you see the charges are compensating the electric field. The negative charges are now being pulled to this side here. And for that reason, the electric field basically is pushed out. And you have here the atoms are getting ionized. So the mobile carriers are pulled away from that side. So you have a surplus of positive charges. And in total, your electric field will vanish inside. Also, you know, if you have a conductor, the electric field line will always enter from outside. It will, on this boundary, it will always enter perpendicular. Why is that? Because it means there can be only, at the interface, there can be only a normal component of the electric field, which makes sense because if you had any tangential component, that would imply at the interface, you would also have inside an electric tangential component. But we just said inside at a perfect conductor, there can be no electric field. So there is no tangential component allowed at the boundary for the perfect electric conductor. And if you have a perfect electric conducting material, you always only have a normal component of the electric field at the interface. So this phenomenon that you get the electrostatic field pushed out of the conductor, this is called the electrostatic induction. So we are approaching, by the way, now the end of chapter 1. We still get to the electric capacitance, some arrangement of capacitances, and then also the energy stored in a capacitor. And so then we will be done. So I think by tomorrow we should be done with chapter 1. We have in total 4 chapters. And as you can imagine, the other chapters are a bit shorter. So one is the longest chapter, then we will have chapter 2. The 3 is a bit longer too, but chapter 2 is quite short also, and chapter 4 is very short, so don't worry. So this covers also a very large part, the chapter 1. So now you have we want to look at the concept of capacitance. You can have two conductors, and they can be arranged so that they're in close vicinity, and then you put charges on these two conductors, and then you have an electric field that is between these two conducting elements. So consider we have two electric conductors L1 and L2, and I will graph them for you here. This shall be some disk like that. This is our first conductor L1, and we have here a second conductor. Shape is arbitrary. I'll make here some cube. This is our conductor L2, and then you put charges on these. On this one you have a charge Q1, which is denoted, which happens to be plus Q, and the Q2 is on the second conductor, that is equal to minus Q. So you have this charge located on a conductor L1 that is called Q1, and you have the charge located on conductor 2, that's L2. So how do you get these charges? Basically, you apply a voltage to these both conductors, and then by doing that, you charge those. So you apply a voltage, and it will yield to some charging. Thank you. So what we are interested in is not in the charging process itself. We are interested in the final process, because in the end, you get into some equilibrium state or situation where there's no further changes happening. While you're charging, of course, there's current flowing, charges flowing, but we are interested what happened once the charging is completed, because you connect them to a given voltage, and after a while you will enter into a final equilibrium state. In this final state, there will be no change with time, yeah? This final state we're looking at. Otherwise, it would be also not necessarily static anymore. You have now an electric field. We have here charge Q plus on conductor 1. And you see what you have to consider is that electric field. Okay, this is a bit tricky. I maybe should not put it on the corner here. Oh, because it would be hard to make a right angle, and corner situations are a bit dicey anyway. So here, anywhere you have rectangular entry and exit points from the conductors for the electric field, respectively the displacement field. So this is our electric field between L1 and L2. The charge Q1, is by magnitude the same as Q2, is Q. How is the electric field inside the conductor? Anyone? Electric field inside the conductor, how is it? Okay, the electric field inside conductor 1 is denoted as E sub I for inside 1. It happens to be the same as the electric field inside conductor 2, and it is 0. It is vanishing because of that electrostatic induction. So the charge is then localized at the surface of the conductor, right? Why is that? Because the charges within the conductor, they try to maximize also their distance to each other, and also because there's a field outside, they will be, they will be pulled from the charges at the respective different conductor, they will be pulled to the surface, and from there on they try to, according to the field, amongst themselves find a large separation so that the forces between them are not getting too strong. So they are localized at the surface of the conductor. And these surfaces, these are equipotential surfaces. That means not only the surface, but the entire conductor has a constant potential. So the potential at the conductor 1 is called phi 1 and is constant. The potential at the conductor 2 is phi 2 and is also constant. They're not the same, phi 1 and phi 2, but they're both constants. And we have here, let's not do this one here. We, however, want to get now the definition, basically, of the capacitance. So you have applied a voltage on these to these two conductors, so charge has flown onto these, and this is trying to, I mean, they exert a force on each other. In consequence, you have the electric field in between these two conductors, and the whole arrangement accounts for a capacitor. We can give a definition of the electric capacitance. You can apply this voltage. You can do a charging of these two conductors, and then you can remove the wires that you use to bring on the charge, and then this charge will be be held by these two conductors, and the voltage also will sustain. This can be also some named as electrodes. And this is given by, the capacitance is given by the charge per voltage between these two conductors. Equation 1.42. That means you apply a certain voltage, you will get a certain charge, and this relation charge to voltage, that is called the capacitance. And this capacitance is basically a function of your geometry. If you increase the voltage even further, then you will accordingly get more charge on these two conductors. And this relation voltage to charge, that is captured in this electric capacitance. The capacitance denotes the capability, describes the capability to store charge per applied voltage. And important to notice, this capacitance, it does not depend on Q1 and does not depend on the voltage you want to either. It is just dependent on the geometry. And so this geometry dependent parameter, that is basically termed the capacitance. It does not depend on Q. It does not depend on U12. However, depends on geometry and on that only. So your capacitance is a function of geometry, maybe geometry only. It also depends on the material that is involved here. So it also depends also on your permittivity of the, also it depends on your geometry and materials involved. This is an example of a plate capacitor, two parallel plates you have, and they have a total area of A, and you now put some voltage there. You connect it here to some voltage source with some wires, and then as a consequence, some charge will flow onto these plates. Here we have set it up that plus charges are accumulating to the left. And they distribute here. Well, they distribute over the entire surface here, but to the surface turned towards the other plate. And then you have electric field lines. You have inside a homogeneous electric field, and nearly all of that is concentrating, but of course you have also field lines like that. But these we denote as stray fields. They will be not the major contributors to the electric field. Inside, so your field is homogeneous, and then, so the plates are charged with opposite charge, plus minus q, resulting into a surface charge sigma 1, respectively 2 on each plate. And now between the two plates, you can also have a dielectric material. So we say that there's a material inside, and this material has a permittivity which we denote as epsilon naught times epsilon r. We have here the separation of the two plates given by d. We say that all is oriented such that this arrow is in z direction. The plates here are located at 0 and d. This here is our stray field that we can often neglect, and that we do also now. We neglect that here, the stray field. Rather, we are working only with a homogeneous field. Then if we neglect the stray field, what remains is our homogeneous field. I mean, this is a specific property of these parallel plate capacitors, where you also assume that the area, the size of this plate here, that it is quite large. The separation is not very large here. And this is a very different scenario from this example here, which is kind of a very random and general example where you will not, well, maybe it is in part here homogeneous, but in overall you cannot assume that you have here maybe some local homogeneous field, but in total you will have not an homogeneous E field if you have an arbitrary shape here of your conductors. But if you shape them and write, or, well, depends on what you want, but for the parallel plate capacitor, this is a very good example, because you will end up having here a nice homogeneous field, and you have not really any stray fields that you usually have to take into account. So the electric field here is oriented in z direction. That homogeneous field means basically that the E field is uniform inside the capacitor, yeah? And we want to calculate now the relation between the voltage, the voltage U, and the charge that is being put on the plates. So what we have to calculate is the voltage independence of the charge, and we know by definition this relation between the charge and voltage, that gives us a capacitance. So what is voltage between plate 1 and between plate 2? That we denote as U12, and we obtain it by integrating from conductor L1 to conductor L2 over the E field, over the differential line element here. But for our parallel plate capacitor, we see our one conductor is located at 0, z equal to 0, and the other one is located at z equal to d. We also assume here that, based on our assumption here, that it only has a z field component, and this assumption is also valid because we know we have a very narrow separation compared to the area. So of the plates, and the field lines are perpendicular out of the conductor. So yeah, this field basically has to be z oriented. So the field is in z direction. And if we look at our line element, that is also then in Z direction, we integrate right along the Z axis, then you see what our vectorial components are thankfully vanishing. Ez dot product with Ez is just 1, and that means we only have to calculate the magnitude of Ez here over the dz, and that in this particular case is thankfully just taking Ez times the distance of the plate separation. So you know that the electric field between these two plates is just the voltage that you apply over the separation of these two plates. Now, what about the charge? The charge is given by the displacement field, like the electric field. It is inside the plate only oriented in Z direction, times the area of that plate. So we know that the displacement field is given by epsilon naught times epsilon 1, by epsilon r. Here that is the material properties of the dielectric material within the two parallel plates, times the electric field times the area. You have here a surface charge on these plates, and that surface charge sigma is charge per area, right? So that corresponds to the normal of the displacement field, the absolute value of the displacement field times the normal of the um, the normal vector on the parallel plates. So this enters basically in here. This is why the dz has only, it becomes here just a scalar quantity. So we have the advantage that we have here constant and also homogeneous surface charge and the surface of the conductor. So the capacitance is Q over the voltage, and we saw the Q is